Hello students, we are diving into the RISC-V ISA over the past few lectures, and what we have seen are some of the arithmetic instructions which had both the logical instructions and the typical arithmetic instructions like add, subtract, etc. And after that we looked at the data transfer instructions, namely loads and stores, and why we need to use them. Following that, we looked at how we can change the control or the flow of execution using the branch instructions, right? And we'll continue further, and we are going to look at some more of the interesting instructions that RISC-V provides. Now, the couple of questions we already faced from some of your friends in the class are how to deal with either addresses or values which are greater than 12 bits. So because the immediate field in almost all the instructions we have seen so far is limited to 12 bits. So how do we handle values which are bigger than 12 bits? So RISC-V provides two instructions. The very first one is load upper immediate. LUI is its mnemonic, and it looks something like this: LUI, RD, and an immediate field of 20 bits. Right, RD is the destination register. What this instruction does is it places the 20-bit value as in the MSB 20 bits of this register RD, and the remaining 12 bits of this register will be zeros. It means the simpler way to understand is it will left shift this 20-bit value by 12 positions and then place it in the destination register. So if this is a 32-bit register, each block representing 8 bits, then whatever immediate value we give in the instruction as part of the instruction will be placed at MSB side, and the lower 12 bits would be zeros. And the format of this instruction used for instruction encoding is something like this. We have the 7-bit opcode followed by 5 bits of the destination register's number. Following that, we have 20 bits of the immediate field. So it is the primary job of the compiler to use this instruction, but as part of module 1, because we ourselves are acting like the compilers, translating some high level language into the assembly language, it is our duty to look at the values that we are using in the program, and if they don't fit in the 12 bits, then we need to use this LUI appropriately, right? And the most common example in RISC-V is the LI instruction. It's a pseudo instruction. You can go through it. I'll give you the reference book also. And a combination of this LUI can be used by loads and stores also. Why not? If you want to get the value from an address, right, where the base register is there, but the offset is more than 12 bits. So we can use a combination of LUI there also. So I'm going to provide the RISC-V summary .pdf book. Do go through the page numbers 58 and 59 to understand how and what LUI is. The second instruction that RISC-V supports is or provides is add upper immediate to program counter. In short, it is AUI PC. It would look something like this, very similar to the previous instruction. We have the AUI PC mnemonic RD destination register followed by the 20-bit immediate value. This instruction also works very similar to LUI, but there's a small difference that it also uses PC. Now, how does it do that? It will first left shift the 20-bit value by 12-bit positions. Then we have the 32-bit value. It will be added to the PC, the current PC, whatever we have, and that value will be written into the destination address. Okay, and it also has the similar format, U format, like the LUI with the opcode, RD, and 20 bits of immediate field. The specific opcode you can check in the RISC-V reference datasheet that I have provided. AUIPC is primarily used by the pseudo instruction LA that you have already seen in your lab 1, right? You can play around with the different values and see how LI is split into multiple instructions, right? Uh, Page number 60 and 61 of the RISC-V summary book talk more about AUIPC and LA instruction. So do go through that. Before I move any further, I wanted to make a quick note about the pseudo instructions. Right, we have seen quite a few over the past couple of lectures. It is primary duty of the assembler to handle all the standard instructions given in an ISA. Only then we would say that we have built an assembler for that particular ISA. Now the pseudo instructions are not standard. So the the assembler is not binded, or there is no commitment from the assembler that it needs to support these pseudo instructions. These instructions are mainly for the convenience of the assembly programmer, right? So there the how many pseudo instructions are supported by a given assembler is heavily dependent on the guy who wrote the assembler itself, right? So for example, in Venus, it does not support all the pseudo instructions that RISC-V has, or people have come up with using the RISC-V, right? It has support for only few. If you want to look at the exhaustive list of or all the instructions and the pseudo instruction RISC-V, you can check the link in this provided here. Very few are supported by Venus, but we can't say that Venus is not for RISC-V, because it still supports all the standard instructions. So keeping this point in view, I am suggesting all of you not to heavily depend on these pseudo instructions. Try to use the native or the standard instructions of RISC-V to get your uh, problems done. Now, don't depend on these pseudo instructions. So the LUI and AUIPC are discussed in section 2.10 of the textbook. In addition, I'm going to share the RISC-V summary document. Go through the specific pages that I have mentioned, because this particular document is nearly 350 pages long. I don't expect you to go through all of them, and whenever the need arises, I'm going to point you to some specific pages. Go through them. That would be sufficient. Okay, moving on. Let's look at some more interesting uh, aspect that we kind of are used to in the high level language. Here is an example. Let's say there is a main function, right? And it has some piece of code, uh, some lines of code. After that, we have a function call to the function 1, right? And after that, we have some more lines of code. Then we call function 2, and probably after a few more instructions or lines of code, we end this function. Now, what we expect when we write such a code is, when the control comes to the function 1 call, right, it will go to the definition of function 1 and go execute it, come back to the main function, and whenever the function 2 is called, it will go to the place where function 2 is there, execute those, and come back. So a quick walkthrough on what would need to happen is we have some sequential lines of code, or it can be a small if else or switch case statements also that don't um, require the control to jump out of the main function. But when there is a function call, what we expect is the control will go to the function one's definition, execute the code there, and that code itself can have uh, all kind of different logics, if else, switch, or loops, anything like that, right? After that function is executed, we expect the control to come back to the line uh, the very next line after function one. Then we will continue, or we expect the hardware to continue execution of some more lines of code, and then when it sees a call for function 2, the control goes to the definition of function 2, executes that, and comes back. Now the question is, which of the instructions that we have seen so far will help us to handle these changes in control, right? We did see some branch instructions, but those will not help us completely, because we expect to come back to the place where the function call was made after some particular function gets executed. Now the branch will not do that job. It can hardly help us to get the control from the function call to the function definition, but not back. So we need something extra, right? The question we are trying to answer in this lecture is, how does the compiler indicate these changes in the control? Basically, how does the compiler convey to the hardware that there should be a change in the flow, right? So let's look at a little more what we mean by a function or a procedure in general. It is a subroutine that we write for to perform a specific task, a very well-defined task, and it would work on the parameters that are given to it, either by reference or by name, anything, right? And it would, after the particular subroutine is executed, we expect a change in some variable or other, which we call the result, and that will be used by the main program. So this subroutine or the procedure or a function is a powerful tool for the programmers to structure their code. It will help in understanding the code better. It will make it modular also, right? And also it will help in reuse of a piece of code, right? We need not we need not write that piece of code multiple times if we intend to use it. If, multiple times, right? We just call it multiple times rather than writing the code multiple times. We write the function just once and call it maybe 10 or 15 based on the logic that needs to be implemented, right? So these procedures and functions are not something we can dispose of with. We got heavily used to these programming methods. So here is another example of abstraction, right? We use the function. There might be some STL libraries that you use day in day out in your programming, but we don't actually know how they are performing the job themselves, right? We expect that the job is done and we are going to take the output of that function and work with it. So yeah, this is an example of abstraction. The parameters that we pass to the function are the key. Typically that's what we are bothered about. Parameters can be the input parameters or the result parameters, right? These can be imagined as an interface between the place where it has been called to the definition. Now let's see how we can write such procedures or functions. While it is very easy, because we got used to it in the high level language, it is not so in the assembly language. Why? Because we need to explicitly handle the data. When we say that I am passing a parameter, in typical high level language, we just write the parameter name. We expect that function will pick the value of that parameter and work with it. But here we need to explicitly say where to pick the value from. So the arguments of the function, the return values, etc. If there are any other data that we want to provide, we need to give explicit instructions for that. Also, the control flow needs to be properly ensured, just like the branch instructions that we saw in the previous class. Here too, we expect the control to go to the function definition, execute it, and once the execution of that function is done, we expect it to come back. Yes, we do expect it to come back, but we need to tell the hardware how to come back, right? So we need to tell it where to come back to. Accordingly, we have some specific instructions for that. So all this will contribute to the extra work for the assembly programmers, in the sense that they need to explicitly handle the control flow and handle the data flow among the function calls. So what are the steps required? Let's go a little deeper. The very first thing is imagine a place where we put all the parameters that we expect the function to use, right? And we also need to make a note of where where the function needs, or the control needs to come back once the function is executed. After that, we transfer the control to the function. That function, you can call it as callee. Within the procedure, we might need to declare some local variables, etc., right? In the typical high level language, something similar needs to be done at the assembly if you want to use some additional variables or anything like that. Perform the function, means execute the function itself, right? And then once the function is executed, whatever the result we want from the function will needs to be placed in a place where the caller, the original program which called this function, or the original or let's say the main program which called the function 1, needs to get the data from. After that, we need to free up this storage that we reserved for the procedure, and then come back to the caller. So here we make use of the information that we stored as point 2, right? So let's go through these from the implementation point of view. Here is just a logical flow. Now the very first question is, where do I place these parameters or variables, anything like that? So the very first thought that would come to our mind is, why not use the registers? So we have 32 registers. So maybe I'll tell that the registers are 10, x10 to x15, right, are for this procedure calling. In some sense, RISC-V also gives some directions with registers usage. It says that registers x10 to x17 can be used for parameter passing and results passing, right? So but this is not a hard and fast rule. It's like a standard uh, um, suggestion from the RISC-V developers. The callee means the function which has been called will place the results in the same set of registers x10 to x17. So when the control comes back to the caller, it can retrieve these values from these registers and start using them, right? Now x1, the register, will be used to store the place of origin, or the very next instruction of the after this function call, so that we can use the value in x1 to come back to this particular instruction and resume our execution in the within the caller program. For this, we have a special instruction which is called jump and link instruction. In short, it is JL, the mnemonic. It looks something like this: JL x1 and the procedure address where we want to jump to. excuse me. What this instruction does is it saves the address of the next instruction. It can be it is the value of the PC in X1, and jumps just like the branch instruction does. It transfers the control from the caller to the callee, or the first instruction in the callee. So you can imagine that X1 would be the link we use to come back from the callee to the caller. That's why it's called return address. So just like X10 to X17 are suggested by the architects, X1 is suggested by the architects to be used as a return address register. So the procedure address that we provide in JL instruction can be the label of the first instruction of that function. And X1, like I said, is a suggestion. You can use any other register, but be careful to reuse it to come back. Okay, so if you fix that X1 is what I'm going to use, stick to that. To support the return from the procedure, we have another special instruction, which is jump and link register instruction. In short, it is JLR, and it looks something like this. So it has two register operands and an offset field. So X10 is again okay. Before that, what this instruction does is it will jump to a location which is given by addition of the register X1 and the offset value 0. So it's like base plus offset kind of thing. Because you already stored the return address in X1, now you can use the same thing here to come back to the main program or the caller. Now you can ask why we want to store the address of next instruction. The next instruction after the end of the function, do we need to use? Typically not. That's the reason we instead of placing X10 or anything like that here, we place X0, because X0 is always 0. We don't expect to come back to the next instruction after the function's definition. Okay. So what exactly happens with JL and JLR is if we have JL X1 proc address, the value in X1 would be the PC plus 4, which is the address of the next instruction. After that, the PC will be updated or overwritten with the value of the proc address. When it comes to JLR, X11, just like JL, will be storing the address of the next instruction, which we typically don't use. But the important point is the value in PC will be overwritten by the sum of X1 and 0, or basically the base register plus an offset value. These two instructions will help us to realize a procedure or a function at assembly. Now, if we want to branch within a procedure, we have seen the conditional branches, right? Based on a condition, we jump to some location or we continue our execution. In the same way, we can use JL, JLR also, but here there is no condition. It is an unconditional jump. Okay, so in fact, we can use JLR also, but then you need the value where to jump to in a register. That would be a tricky point to get. So instead, we can use JL and jump to the label of that particular instruction, right? So JL X0 and label. This is the pseudo instruction J that you would have seen in lab 1. Now here is a hint of the question you will get in lab 2 is realizing the switch and case statement using the branch table. I have already mentioned how we can use the branch table but here is the implementation hint, you can say. You can use the JL instruction and jump to the label. So this label would be the address that we get from the branch table. So try it out, we can discuss. Now, again, if you want to pass more parameters from one function to another function, let's say, how do we do it? Here we have only 7 or 8 registers, right? In that case, maybe we can use the other registers, but before we use the other registers for this function call, we need to store them into the memory, right? So that when the control comes back to the main function, we can restore the same values. Let's say I want to use register x20 also, and the value of x20 is, let's say, 50. So the value 50 needs to be stored in memory, right? And then x20 will be used within the function. When the control comes back to the main program, let's say, then we need to restore this 50 into x20 so that we'll not have any problems later on with the instructions that follow this function call. Okay, so this will introduce additional load and store instructions, and this is a classic example of register spilling, right? What happens is a value and in a register is placed in the memory and retrieved in a short while, and this is happening multiple times because we are dealing with a lot of variables at a time, which can be typically more than the 31 registers provided by RISC-V. Now, where do we save this spill data? Is I mentioned that it's memory, but then if you want to store in the memory, to load it back, you need the location where you have stored, right? To make the life simple, the architects provide what's called as a stack memory, right? What is the main advantage of stack is we don't need to explicitly store or keep a note of where this uh, value is stored in the memory. The stack pointer, SP in short, will help us with it, right? So uh, that's what I explained. The using the memory directly has a disadvantage. So I'm going to talk about the stack, how it's laid out, and how do we use it, and how much it will help in the realization of a function at the assembly in the next lecture. Okay, the contents of this lecture can be found in section 2.8 of the textbook. With that, I will pause this lecture and we'll continue more with function or procedure execution in the next lecture also. Thank you.